So I'm going to talk to you about the solid Earth and oxygen, and I'm violating one of the principles that I learned as a graduate student, which was that there's nothing wrong with the sediment that 1,000 degrees and 5 kilobars wouldn't fix. But it turns out that if you do that to sediments, you do terrible things to them, and you lose all the wonderful information about this story of oxygen. And so I'm going to drop down to lower temperatures and try and talk about what's happening at lower temperatures at ocean ridges and how that might be important in the oxygen budget, and also make some general observations from a naive petrological person's perspective, because in our world, life is so much simpler. In the low-temperature world, life is so complicated. I understand why I went into high-temperature geochemistry originally. So there are big questions, of course, that all of us are familiar with, and hundreds of papers have been written on them, which is, what is the history of oxygen in the atmosphere over time? Why is oxygen buffered at constant levels and maybe at different levels in Earth history? Have there been events in the change of oxygen over time? So there's sort of short periods of time where vast changes have occurred. And since life is making oxygen all the time, why is it that the mantle hasn't become more oxidized through time? And what's going on today? And can we understand why it is that the atmosphere is at 21% oxygen today and hasn't been changing much for hundreds of millions of years? And then how does the consideration of what's going on at ocean ridges contribute to these kinds of issues? So in writing or revising How to Build a Habitable Planet with Wally Broecker, we needed to write about oxygen. And I realized that actually it's a much more simple problem, or can be phrased much more simply than it's often phrased in the literature, which is that it's simply a matter of mass balance between net oxygen production, which comes from burial of organic matter, and the way this oxygen that is produced is consumed during Earth history. So currently, even though there's lots of oxygen in the atmosphere, even though oxygen is being buried in sediments as we speak, nonetheless, oxygen in the atmosphere is remaining constant. So there's no net oxygen production today. Interesting thought. So the sources of reduction are the burial of organic matter, or the loss of hydrogen from the top of the atmosphere. And I'm not going to talk about that at all because it frustrates me, because as far as I know, there's no way to measure it. So I view that as sort of an unknown free parameter, which I'm not going to be considering. And the sinks are the oxidation of the organic matter, the oxidation of iron, and the oxidation of sulfur. Of course, there's oxidation of minor elements too, but volumetrically that's not so important. So we can sort of summarize these in schematic reactions like these. In the top one, this is written as the oxidation of organic matter, but of course photosynthesis runs it in reduce, producing organic matter and free oxygen. That's the production term. And these are the consumption terms. You can oxidize the iron from ferrous to ferric, you can oxidize the sulfur, and those are consuming the oxygen that was produced by the photosynthesis. And so what we want to be able to do is to track those two things through Earth time and figure out what the balance of them has been. The balance of oxygen production, this one moving to the left, the balance of oxygen consumption, all four of these moving to the right. So the rise of oxygen, the creation of what we call the planetary fuel cell over Earth history, is just the evolution of these reactions and how they've changed through time. And that's led over Earth history to a situation that allows us all to be here today, which is we have a planetary fuel cell with a completely oxidized surface with 21% oxygen in the atmosphere and the reduced molecules. And we operate this fuel cell by eating and breathing. We operate it now. It's operating through weathering. It's what makes advanced life and civilization possible. And that has happened by taking the initial oxidation state of the Earth and splitting it in two to create the oxidized and the reduced reservoirs. And the oxidized reservoir is out here on the surface, and the reduced reservoir is in the interior. That would include organic matter buried in sediments. And so if you look at it in this way, you realize there's no way that oxidation of the exterior can ever oxidize the interior of the planet, because there always has to be mass balance. So the amount that the exterior is oxidized means the amount someplace else needs to be reduced. So it's not possible for life to oxidize Earth's interior. So with the exception of the unknowable hydrogen loss, there's going to be mass balance, and that's what I just said. So let's look then at the global mass balance over Earth history, and there needs to be a balance between the amount of oxidized material in oxygen equivalents and the amount of reduced material in oxygen equivalents. So here are the various reservoirs of carbon, and the orange bars are the reduced carbon, and the green bars are the oxidized carbon. And you can sum them all up to see how much organic carbon there is. And there are various estimates from that, not made by me, but made by others, that come out to between 600 and 1250 times 10 to the 18th moles, or examoles. So that needs to be balanced by the oxidized reservoirs. So here's the total amount of oxygen that's been produced by organic carbon based on the amount of carbon we can see that's been buried. There's the tiny amount of oxygen in the atmosphere. Here's the oxygen in sulfate. There's the oxygen in ferric iron. And there's the total oxygen in oxidized compounds. So there are two things from this that it seems to me are obvious but are not really acknowledged that much in the literature. The first one is that iron is overwhelmingly the most important sink for oxygen that's been produced by organic matter. And the second is that we have a mass balance problem, that the size of this column, O2 production, and the size of this column, O2 consumption, should be equal, and they're not. So we're missing a reduced reservoir somewhere. Where might that be? So one question is, why is iron more important than sulfur? And if you read a lot of the literature, iron and sulfur are treated in terms of pyrite. And if you look at pyrite, it's FeS2. And the iron goes from 2 plus to 3 plus. That's a 1 electron movement. And the sulfur can go from -1 or -2 to +6. So that's 14, 15, 16 electrons. So it's a 16 to 1 sulfur more important than iron. That's because there's not the recognition that, well, actually the iron in the sulfide is trivial compared to the total amount of iron in the rock. So if you look at the iron to sulfur ratios in the continental crust, and turns out about the same in the oceanic crust, they're about 60. So even with this 8 to 1 electron difference, the effective ratio is about 10, about 8, and therefore this makes iron, if all of it were oxidized, 8 or 10 times more important than sulfur. Not all of it is oxidized, so it's a factor of 3 or 4 more important than sulfur, which is why we have this difference in the relative numbers of electrons that are accounted for by sulfur and by iron. So how are we going to account for this mass balance problem? It implies there's a large reduced reservoir somewhere, and that could be subducted organic carbon or hydrogen lost to space. And a way of thinking about this, and I have been very influenced by this paper by Hayes and Waldbauer in 2006, which is a wonderful paper. And they propose that basically you can track oxygen production through time by just recognizing that the fraction of organic matter relative to the CO2 outgassing has been relatively constant over time. And in that case, you can make estimates for CO2 outgassing, and that gives you a flux of oxygen into the external world over Earth history. And so this line down here shows the progressive change in oxygen accumulation at the surface over time. Well, because the Earth was more volcanically active, convection was more vigorous earlier in Earth history, the thought is that maybe oxygen production was higher in the past than it is today. But we can take today's value as a kind of minimum value, and we can extrapolate that back over Earth history and calculate how much organic carbon should have been produced if we do that. And it turns out, if you do that, that the total amount of carbon that should have been produced, organic carbon, vastly exceeds the organic carbon current surface reservoir. So at least 4 times more organic carbon burial than observed. What's happened to it? It turns out that the net organic carbon that's buried at the surface is almost exactly equal to the amount of carbon that's buried in pelagic sediments. So those pelagic sediments then get subducted. They get subducted along with carbonates, so they're going down in some proportion that's, roughly 20% like the carbon isotopes would say. And over Earth history, this subduction has to be progressively happening with time. And so we're just accumulating organic carbon in the mantle. Now, is that important to the mantle oxidation state? No. Because if you look at the total amount of organic carbon, you find that, this is a log scale over here, you find that it's less than 1% of the total amount of carbon in the mantle. So you're making a very slight reduction of Earth's interior as you oxidize the exterior, but not so much as you would be able to measure it. So the next question I want to address is whether there were great oxygenation events, or oxidation events. And this is a figure that you'll see in many places, though in the recent literature it's being questioned more. Particularly people who were fans of Snowball Earth episodes like the idea that there were apparently Snowball Earth episodes about 2.2 billion years ago, and in the Neoproterozoic about 700 million years ago. And there might be some relationship between these glaciation events and step rises in oxygen. So you'd have a low value of oxygen, and then there'd be a step at the first snowball event, and then another step at the second snowball event. These would be great oxidation events, the GOE and the NOE. Okay, so this bothers me philosophically. It bothers me because, as a sort of a general view, it seems to me that life is what planets do. Life maximizes entropy production, and life ultimately leads to progressively better processing of energy and more extensive relationships. And so planets undergo an evolution, sort of like ours has, given the opportunity. So this, I would think, would be a natural process of planetary evolution. If it depends on Snowball Earth episodes, we're screwed in terms of being able to communicate with other intelligent beings in the universe, because that makes our situation so incredibly unique if you require Snowball Earth episodes to get rises in oxygen. So it seems to me there ought to be something that's much more general in terms of increasing the oxygen through time. Of course, that doesn't mean it didn't happen that way, but I just did some simple thought experiments and a simple numerical model that if we can choose your growth curve for total oxygen production through time, you're always degassing, you're always burying organic carbon, so you're steadily producing oxygen at the surface. And then might it be possible, even with a steady and a continuous production model, to generate steps in O2 in the atmosphere? And I'll show you in a second that this is actually a very simple thing to do with the simple first-order rate model, so that you can have a steady oxygen production and steps in the oxygen in the atmosphere. Now, unfortunately, we can't measure oxygen in the atmosphere. We're watching the play of Earth history. And in that play of Earth history, oxygen is the protagonist, and it never comes on stage. Instead, we're having to deal with all these other things that we're measuring for oxygen, the various proxies. And these proxies have thresholds. So we could imagine a step function in oxygen in the atmosphere, or we can imagine some kind of continuous fraction. And there's going to be thresholds for the proxies. And it could be that these thresholds would be crossed during great oxygenation events, or it could be that there's a steady growth of oxygen, and we simply cross the threshold at a certain period of time, and that changes what we see in the signal. So, silly analogy. You take a beaker, you have water in it, you're adding water and you're adding a little salt. You add the water and the salt at some sort of rate, and so the salt is continually dissolving in the water. But you're adding the salt a little bit faster. So at one point, the water becomes saturated and the salt starts to precipitate. This has been a completely continuous process. But if you're looking at a proxy of when does solid salt appear, you would say, oh, there was a big salt event that happened when this salt started appearing at the bottom of the beaker. But it wouldn't have anything to do with the actual processes that were going on. So what's the evidence that we see for these kinds of significant events? One comes from banded iron formations. This is the compilation from Isley and Abbott. And they did an analysis of the abundance of banded iron formations through time. And another is the wonderful data from the sulfur mass independent fractionation, showing this abrupt change between 2,400 and 2,500 million years. And if you plot those on the same diagram, you see that this termination of the mass-independent isotope fractionation corresponds exactly with this break in the iron formations. It's true you do have another episode at about 1.8 billion years, but I find the coincidence of those two signals remarkable. That suggests to me maybe there actually was an event at that time. But the original argument for the great oxidation event came from the oxygen isotopes. And the oxygen isotopes show this bulge in the del C13, and that was presumed to reflect more organic matter burial and therefore a high level of oxygen production. So if that tied in with the evidence from the iron and the mass-independent isotope fractionation, everything would be great. But it doesn't. The isotope excursion occurs a few hundred million years after the SMIF and banded ion formation, SMIF and BIF, signals that you see from these other two proxies. So there's no apparent connection between there. And we're talking about a 300 or 400 million year time period. That's essentially all of the most of the Phanerozoic. And so this is a vast range of Earth history. I think the evidence for a particular oxidation event driven by burial of organic carbon is extremely tenuous. So let's consider how something might work in a very simplified way. And of course, I recognize the extremely sophisticated models that have been done of this process, and this is not one of those. So it's more like a thought experiment. That we have O2 production, that's just happening from the burial of organic matter. And we have some reservoir where the interactions are taking place, the atmosphere, the ocean. And we have a flux of reduced elements going into that reservoir, and there's going to be a reaction between those two such that the oxygen is consumed and the reduced element is consumed, and the length of time that that reaction is going to take place is going to depend on the relative rates of these two things, the kinetics of their reaction, and the volume that there are in the reservoir. Now, provided the oxygen production is greater than the flux of the reduced element, ultimately you saturate the reservoir, and then oxygen is able to build again. So if you set this up with a simple set of equations, you can set up relationships like this, where the oxygen grows. Now all the interaction is taking place in this common reservoir. Ultimately the reservoir gets saturated, and then oxygen ascends. This is with completely steady oxygen production through time. So let's think what the potential sequential reservoirs are. After you've saturated one, you build up oxygen, and then you can start having interactions with another. The first one would be the reduced gases in the early atmosphere. They're going to be an important sink for oxygen early on. Then there'll be the oxidation of the continental crust. Then we're going to need to oxidize the ocean, and as we'll see in a minute, then once the ocean is oxidized, then we can oxidize the ocean crust. And you can see that different aspects of these actually have to pass certain thresholds in order to access the new reservoir. For example, you can't access the ocean crust reservoir until you have oxidized materials in seawater. All right, so what is this ocean crust oxygen sink? If you go to sea and you dredge up the salts from the seafloor, they come up flashing black jewels. And sometimes you pull up an old rock and it's green grunge. And if you drill into the ocean crust, you see all this alteration, red, green, tan colors. And this is from one of the drill holes in ocean crust. You can see the veins. This is oxidized material around the veins. You can see these patches of discoloration. And so it's possible to go and make measurements of how much ferric iron there is. This was done by Langmuir and colleagues back in 1999. And I was thrilled to see at this meeting that people are now doing it more carefully. So Mary Jo Brounce had a very nice talk, 2 days ago, in which she'd done an analysis of one of the deepest holes for ferric iron content. So this black bar is the value of ferric-ferrous ratio for fresh ocean ridge basalt. And these are her measurements on the ferric-ferrous ratios of the material going down to 900 meters. There was another talk by a woman working over in England who also had data going down to about 1.2 kilometers. And you can then see what the difference is in the ferric-ferrous ratios. That pristine morb has a value of 0.16, and if you look at the supercomposite from this drill hole, it has a ratio of ferric to ferrous of total iron of 0.51. That's for 1,200 meters of ocean crust with about 10% ferrous iron in it, of which 5% is being converted to ferric iron through interaction with oxidized materials. All right, so using these new data, I could redo the numbers and look at the actual fluxes of oxygen that have to go into the crust in order to produce this change given the overall crustal production rates. And it turns out that if you take the current burial rate of organic carbon of about 0.7 times 10 to the 12th moles per year, the amount of oxygen going into the ocean crust is about 3 times 10 to the 12th equivalent moles. That is a factor of 5, 4 to 5, larger oxygen flux going into the ocean crust than the total amount of oxygen that is being produced by burial of organic carbon. So this suggests to me, first of all, there's some problems, because it turns out if you do this over tens of millions of years, you'll start lowering the oxygen in the atmosphere by a few percent. But what it suggests is also there's a plate tectonic feedback on oxygen, like I was describing for this sequential setting of reservoirs. The last stage might have been that oxygen builds up in the atmosphere until the ocean becomes oxygenated. That is, until it's fully, the sulfur is fully in the sulfate form, and you also have free oxygen dissolved in seawater, currently about 300 micromolar. So that material, once it becomes oxidized, then can cycle through the ocean crust, and suddenly there's a whole new sink for oxygen production. So you build up the oxygen, you saturate the ocean, you open up a new sink, and that then takes the oxygen down and prevents it from rising further. And I think that's a likely reason why the ocean today is right at this boundary between oxia and anoxia, that there's certain times over the Mesozoic and Cenozoic that you've had these oceanic anoxic events. That means the ocean is close to being anoxic. There are parts of the ocean that are anoxic today. We have the Black Sea. So all of this suggests that the ocean is right at this threshold. Why would it be at that threshold? Because that threshold moving up and down is influencing the oxidation of the ocean crust, and thereby is providing this feedback on oxygen. So to reflect, I think the mantle was slightly oxidized early. It had a little bit of ferric iron in it for reasons that we didn't go into in this talk. And it's probably maintained that state within tight bounds. You can't oxidize the interior of the Earth by life on the outside, because then you have a mass balance problem. Also, if you take the amount of oxygen that's produced even in the ocean crust today, even it's been produced for the last 600 million years, it's a trivial amount of oxygen going down relative to the amount of iron in the mantle, and you're also subducting reduced carbon at the same time. So life did not oxidize the mantle. It must have slightly reduced the interior. A steady oxygen production can produce sequential steady states of atmospheric oxygen with very simple reservoir models. And a steady change in atmospheric oxygen can produce sequential steps in proxies, which are not necessarily indicative of oxidation events. They could just be passing particular oxidation thresholds. Oxidized iron is the most important sink for oxygen. And the flux of oxygen to ocean ridges today appears to exceed the net oxygen production from carbon burial. Therefore, it's very possible that there's a feedback between seawater and the ocean crust, which is an important control on oxygen and is the latest stage of this sequential series of reservoirs that are being influenced by the progressive oxidation of the planetary surface. Thank you. So we have 5 minutes for questions.
Step forward with a question or a comment. Oh, there's one.
This is Mary Jo.
Hi. Hi, Charlie. I liked your talk. The case that I presented for the Pacific Plate at ODP 801, do you think that that is maybe an end member case in terms of the oxygen content of subducting slabs that are going down today? And if you were to look off board of maybe Cascadia or the Pacific Northwest, that it would be very different or affect this calculation you've done?
Well, the other data that were presented in the poster that I saw yesterday had a ferric-ferrous ratio of, I think, about 0.35. Okay. So that's more similar to the Langmuir value. So it could vary by about 50%. I think it's a great question to try to find out more quantitatively, try to estimate how much oxygen is being consumed. The other thing I think that would be really interesting is to understand better the reactions that are oxidizing the ocean crust. What's the role of free oxygen in the seawater, and what's the role of circulation of sulfate? As you convert sulfate to H2S, you could be oxidizing the iron. What are the detailed reactions that are occurring during hydrothermal flow?